high. In calculating limits, the main difficulty lies in indeterminate forms. One of the most significant is the form 0 over 0 or infinity over infinity. Among all possible calculation rules, the one that undoubtedly captures students' attention the most is the Hopital rule, often expressed in the following way. The limit of the ratio f of x divided g of x when x goes to x star coincide with the limit when x goes to x star of the ratio of the derivatives f prime of x divided by g prime of x. Under certain conditions, this is indeed true, but precisely under certain conditions. So let's delve deeper into the matter. Let f and g be two functions defined in a neighborhood of a point x star that can be finite or infinity. Assume that both functions go to 0 or infinity when x goes to x star. They are both differentiable in a neighborhood, except at most point x star when we do not need that they are differentiable. We assume also that the g prime, the derivative of g, which is the denominator here, is different from 0 on that neighborhood, except at most at point x star. Then, if the limit of the ratio of the derivatives f prime of x divided g prime of x equals L, finite or infinite, then the same happens for the limit of the functions f of x divided by g of x. The key aspect to consider is the implication. If the limit of the ratio of the derivatives exists, then also the limit of the ratio of the functions exists and they have the same value. A very common mistake is to think that the limit of the ratio of the functions and the limit of the ratio of the derivative, they are just equivalent. So one of them exists if and only if the other exists. This is entirely false. Let's show this through an example. We consider here the limit for x going to plus infinity of 2x plus sine x divided by 2x plus cos x. Easily we see that this is an infinity over infinity indeterminate form, because if we take, for example, numerator 2x plus sine x, and we factorize the 2x, which is bigger here, we have 2x times a parenthesis that is made by 1 plus this fraction, which is bounded divided something that goes to infinity, so it goes to 0. Therefore, these parentheses can be assimilated to a quantity that just goes to 1. So we have that this is 2x times something that goes to 1, and therefore it will go to plus infinity. The same happens for the denominator, and when we do the ratio, we see that these 2x factors, they just simplify, and we remain with the limit of a quantity that goes to 1. So we can conclude that this limit exists and it is equal to 1. But what happens when we try to apply the Hopital rule to this? We have a numerator, both the numerator and denominator, they go to infinity. They are both differentiable. And about the denominator, the derivative of the denominator is 2 minus sine x, clearly greater or equal than 1, so never equal to 0. But when we try to compute the limit of the ratio of the derivatives, we get this limit, which does not exist. So what is the conclusion? The conclusion is that we cannot just apply the Hopital rule, because we have that the limit of the ratio of the derivatives does not exist. But this shows also that the limit of the ratio of the fraction f of x divided the g of x can exist without the limit of the ratio of the derivatives existing. This is to keep in mind. Now let's show an example where things go nicely. Here we have the limit for x going to 0 of x minus sine x divided x cubed. This is, by the way, interesting because it would be impossible to compute this limit without using differential calculus. So here we apply Hopital rule. We call f of x the numerator, x minus sine x, that clearly goes to 0. It is differentiable with derivative 1 minus cos of x. Denominator is x cubed, which goes to 0 as well, and the derivative is 3x squared. Now notice that this derivative can be 0, actually, but this happens at point exactly where we have to compute the limit. So we can say that everywhere else the derivative is different from 0, and that's exactly one of the hypotheses about the denominator. Then, when we compute the limit of the ratio of the derivative, we get this limit, which is, apart from factor 3, a fundamental limit, the limit of cosine. And therefore, easily, we get 1/6. We conclude that, because of the Hopital rule, the limit of the fraction f divided g is equal to 1/6. A consequence of the Hopital rule is a popular differentiability test. It states that if we have a function f which is differentiable in a neighborhood of a certain point x star, where we want to check differentiability, so we don't know yet if f is differentiable at point x star, but we know that at least f is continuous at point x star. We remind that continuity is weaker than differentiability, so it's a necessary but not sufficient condition to be differentiable. Then, if we have that the limit of the derivative exists, and it is equal to a finite value L, the function f is differentiable at point x star, and the derivative equals just this number L. This fact follows easily from the Hopital rule, because when we write the limit to compute the derivative of f at point x star, we recognize that we have a 0/0 indeterminate form. The denominator goes to 0. Also, the numerator goes to 0 because of the continuity at point x star. This argument goes to x star, so f of x star plus h will go to f of x star, so the numerator goes to 0. We try to apply the Hopital rule, and we say that this is a conditional identity, the limit when h goes to 0 of the ratio of the derivatives with respect to h, which is here the variable. When we differentiate the denominator, we get 1. When we differentiate the numerator, we get f prime of x star plus h. But this is just the limit of f prime when the argument of the derivative goes to x star, and therefore it is equal to L. And this finishes the little proof. However, since this comes from the Hopital rule, the application of this test should be made, as the ancient said, cum grano salis. That is always reminding that this is just a sufficient condition. We can see this in an example. Take this function, f of x equal to x squared sine 1/x for x different from 0 and 0 for x equals 0. And we wonder if this is differentiable at x equals 0. Applying the definition, we have to compute the limit of the incremental ratio. If we plug the function inside, f of 0 is 0, this is f of h, which is h squared sine 1/h. We get this, and after simplifying the h, we get this. Now, this is a product where h goes to 0, and sine does not have a limit, but it is bounded, so the product will have limit 0. And this leads to the conclusion that the function is differentiable at x equals 0 with derivative equal to 0. However, when we try to apply the differentiability test, notice that since we already know that the function is differentiable, we know that the function is continuous, so we are in the context of the theorem. When we compute the limit of the derivative of f is given by this formula. We see that a part of the derivative, which is this 2x sine 1/x, goes to 0, so nice. But another part, you see that this x squared cancels with this x squared, is equal to minus cosine of 1/x, which has not a limit when x goes to 0. So we conclude that there is no limit for the derivative. Can we say that the function is not differentiable at 0? No, we proved that it is. So this is just normal, considering that that differentiability test provides a sufficient condition in order to be differentiable. Well, that's it. I hope that this video has been useful and helpful for you to understand better how Hopital rule works. Now it's your time to do something, and I propose you, of course, to practice the application of Hopital rule in computing limits, but also trying to discuss some theoretical question like this one. Good luck.